Something to add as we move away from the mouth, this oral cavity. One thing I didn't mention, one other job of this, aside from the chemical digestion and the mechanical digestion, is also absorption. Remember, we need to be able to absorb into the body tissues themselves. The mouth isn't a huge site of absorption, but you can begin to absorb certain drugs if you take them sublingually below the tongue. So even though we were talking primarily about physical breakdown, there is some absorption that I didn't want to skip past. After I'd cut the last video off, I thought about that for a minute and thought, oh, let me add that on, along with one last thing. I talked about salivary amylase. And keep in mind what we're going to do is we need to break down, ultimately as we go through, starches and carbohydrates. Here we go all the way back to those four big biomolecules: carbohydrates, proteins, lipids, and nucleic acids. So every time you eat an apple, you take in a lot of DNA and RNA as well. So we need to systematically go through and dismantle each one of these. One that I forgot to mention before I got rushed off that last video is lingual lipase. Lingual for the tongue, lipase for lipids. So amylase for starch. Amyl, essentially it translates into white or starch, which is what starch happens to be. So we've got a little bit of a breakdown of lipases and fats. So physical degradation, breaking down some of the starch, breaking down some of the fats and the triglycerides, and a little bit of absorption. Here's something you can do if you don't believe me on this one. I like to point this out in my Bio 101 classes. If you want to actually understand and experience how amylase works, go and take a couple of saltine crackers, preferably without salt, pop them into your mouth and start doing the digestion. So chew them up, smash them against the hard palate, let the saliva interact and intermingle, and don't swallow, which really sounds gross, which is why you probably should not do this around other people. And just keep chewing. Just work it up into a mash. It's going to become a bolus anyway. So once you've done that, what I predict is going to happen in a matter of 5-6 minutes is all of a sudden you'll taste sweetness. Simple sugars, monosaccharides, disaccharides tend to taste sweet. Starch does not. So all of a sudden you're going to start to pick up some of that sweetness. And you might wonder, where's it coming from? It's coming from the activity of the salivary amylase. Another spot before I move on to the next slide of an intersection. Anytime I talk about the tongue, I want to talk about those old, outdated taste maps. Hopefully when you had 271, if you had 271, and you learned about the taste maps, where on the tongue you taste sweet and where bitter, it's not true. So flush that out, put that behind you. So what we've done is we've broken things down. We've started the chemical digestion. We've done a good job on the physical digestion. Now we have to toss it back using the tongue. It's not easy to swallow if you don't have a tongue to use. So if your tongue is numb due to a dental process or procedure, it becomes a little bit more difficult. But once your body has decided that has been broken down enough that I can handle this without choking, you're going to push it back through the pharynx into the esophagus. Now the esophagus, there's not a lot exciting going on in the esophagus. There's no absorption, no more physical breakdown. Might be able to bring a little bit of that in. I'll explain why in a minute. It's essentially just a hose. It goes from the upper esophageal sphincter down to the lower esophageal sphincter. That's when we get to the point past, going inferior to the diaphragm and dumping the contents into the stomach where a lot of stuff is going to take place. Now, what I want to point out, I don't want to pass this up, the lower esophageal sphincter is also referred to as the cardiac sphincter. You might go, why is it a cardiac sphincter? Because that implies the heart. The heart is located right back in here, and that's where the term heartburn comes from. This is a vat of very low pH hydrochloric acid intermingled, commingled with enzymes. You don't want it doing what's called reflux up in through here. If it does reflux up above, superior to the lower esophageal sphincter or the cardiac sphincter, it burns because you don't have the protection in the esophagus that you do around the lining of the stomach. So if you're thinking, wait a minute, I've got a text that calls it the cardiac, I've got one that calls it a lower esophageal, which one do we go with? Either one. Now, how do we get to the stomach? Because I want to talk about the esophagus, I want to talk about the stomach, and then I want to get ready to move on past there into a whole bunch of chemistry. It's what's called peristalsis. Now, if you wonder, wait a minute, I thought it was just gravity that pulled a chewed up Kit Kat down towards my stomach, then you would have a real big problem if you're an astronaut on the International Space Station and somebody hands her a Kit Kat bar and says, there, knock yourself out. She could chew it up, but she'd never be able to get it to the stomach. Conversely, I could offer you $5 if you could hang upside down on some monkey bars at a local playground and eat half a Kit Kat and swallow it up. And you'd take my $5 because you can. The process is called peristalsis. Peristalsis is due to the fact that we have smooth muscle rings that go around the esophagus. Here's that term bolus that I've been hinting at, because it's no longer really food. It's chemically being broken down and it's pretty well mashed up, hopefully by this point. Now what will happen is if you look up where the arrows are, they're going to contract. When they contract, they'll push the bolus down. And then follow the arrows down. They contract, they push the bolus down. Here's the stomach. Follow the arrows, they contract and they push it down. This is the process of moving through the esophagus, and it's not the last time we're going to see it. We're going to come across this process again as we try and move what's left of this bolus through your digestive system. You more than likely have experienced reverse peristalsis. Reverse peristalsis is where all of a sudden this is going in the opposite direction and you vomit. Your body has decided there's something in there that I don't want in here, and so it goes in the opposite direction. It'd be great if you haven't experienced that. But if you've ever been around a little baby, they can have some pretty intense projectile vomiting. I've seen it once, and then I think I probably went and vomited too. So let's get into this. Let's get into this stomach. We get past this lower esophageal sphincter, aka the cardiac sphincter, and now we get into this vat. Now this vat has got a number of things going on. I'm not going to be worried about you knowing the lesser curvature and the greater curvature in the body and the fundus and things like that. I don't think that's really that important. What I want you to see is this. Oh, good. This one's got cardiac sphincter. Your bolus ends up in here. And we now have multiple layers. The first layer, and I'm going to show you an image of this at a microscopic level, is lined with rugae, R-U-G-A-E. So we've got this rugae that is going to increase surface area. There's a nice protective layer that's going to keep the acid, as you're going to see, I think, in the next slide or two, from burning through. Not good if it does. This is where we tend to end up with ulcerations. Ulcers, we thought for a long time, was purely due to us producing more hydrochloric acid. We now know that's not always the case. It's bacterial infection. I'll try and get back to that at some point. But then we've got oblique muscles, we've got circular muscles, and then we've got longitudinal muscles. If you've ever experienced your stomach growl, it's because you got hungry. And all of a sudden this muscular organ starts to contract and move. So what it wants to be able to do is the bolus in here, it wants to mix around and be able to get it in contact with the cells of the rugae. Now why? Oh, and I thought I would throw on this gross little real image of what it really looks like instead of a computer animated. Let's add more digestive enzymes, and I use the term enzymes loosely. I tried to italicize hydrochloric acid, but it didn't italicize real well. That's not an enzyme. Salivary and lingual, stomach. Then pepsin. Pepsin is going to be breaking down protein into polypeptides, smaller chains of amino acids. So we've got our starches being broken down, carbohydrates, we've got our lipids being broken down, we've got our proteins being broken down, and this is all being done at the chemical level. Continually mixing it around, getting it in contact with the rugae. Now, what's the deal with the HCl? HCl is going to be involved in breaking things down. You don't want to play around with a pH of about 2. It will burn you, but we all have it inside us. And we have these pits, these glands that come down. And this is where we look at the lining along these rugae. And what they've got are parietal cells, and these parietal cells just crank out hydrochloric acid. Just kind of bizarre. But it's not just to go in and indiscriminately break down what you just brought in via peristalsis in the form of the bolus. It's also to make sure that the pH is optimal for these digestive enzymes. So all of these enzymes are coming into an area that is very, very, very low pH. That gets interesting because when we leave the stomach, we've got to be able to enter into other structures that really don't like a really low pH. What I did on this is I jumped from here. This is one of the parietal cells. You can see the phospholipid bilayer. This is a proton pump, otherwise it is a acid generator. Don't just ignore this in lysosomes interior. I don't know why that's on there. But what Nexium does is, if anybody is on Nexium, it blocks this pump. It's a big protein that pumps hydrogen ions from inside the cell to outside. This is how we help to maintain a very, very low pH. You can take something like an antacid, Tums, Maalox. All that does is, if you think back to pH, and we'll talk more about it in a couple more videos, it's an OH hydroxide plus a hydrogen ion gives me water. So something like Maalox or Tums just negates this acid just down to water. What Nexium and some of these drugs will do is they will stop the pumping of the acid out into the lumen of the stomach in the first place. So when we start thinking about, about drugs, treatments for problems like heartburn, now hopefully if you didn't know, you know why it's called heartburn. It all comes down to, or often comes down to, the chemistry and the biochemistry of the digestive system. So after this one, I get to a big blank slide. I want to leave the stomach, do some gastric emptying into the rest of the digestive tract. And I think that there's a lot that's going to go on in the next video that I'm going to make. I mentioned that, hey, this low pH it doesn't play well with the rest of the digestive tract. So therefore, we have to get these accessory structures in here. We have to bring in the pancreas, which also brings in blood glucose regulation. We have to bring in the gallbladder, which is a little storage bag. Maybe some of you have had it removed. We have to bring in the liver, and there's going to be a whole lot of chemistry going on in these three spots. They're all going to essentially dump into this digestive tract. From there, we'll get to the large intestine, small intestine, and get to the end of this whole thing where we all know where it ends. So with that being said, let me kill this, and I will be back leaving the stomach.